Hello. Hi. So in this video, I'm going to discuss chapter 22, electric field. In my opinion, this electric field is what makes physics really interesting. So far, what we have done was everything was measurable. It's what we see, and we define the variables, and clearly we can predict. Using that definition, we can predict what's going to happen in the next step, and we can analyze it and all that. That's how we have been, defining the variables. But now we're going to define electric field. But electric field is something we cannot directly see it. It's something that we define it and it's clearly there, it makes sense, but it's not something that's there that we can feel it directly. So what is it? What is electric field? To define the electric field, we have to use something that we already know, electric force. Let me go into the whiteboard. See you over there. Here. Okay, so we're in chapter 22 here. Chapter 22. And this video is about electric field. So what is really electric field? What we know is electric force. We know how to measure electric force. Electric force, which is also known as a Coulomb force, right? Coulombs. How do we measure the Coulomb force? When we have two, so let's say this is the charged particles. And then this is the another charged particle. It's here. Ooh. Okay. Sorry about that. Okay, another charged particle here. They're separated with the distance r or d. Let's do r. So that's the distance apart. So then we say electric force on the Q, big Q, and the electric force on the little q is the same. Electric field E, K, E, the constant, big Q times the little q naught divided by what? R, what is it? R squared, inverse square law. Is that right? What we are saying is that electric field, sorry, and I think it's because I'm holding up on it. Electric field is, so this is the electric force. We're going to define the electric field now. Electric field is E, which is the electric field. That's equals to, so what we're going to do is to take out this little q naught outside. Q naught. Oh, maybe I shouldn't have done that. Let me see, before this, sorry. I want to say what it is that electric force now is equals to, take out the little q naught and this KEQ divided by R squared. And this is the electric field. Electric field. So the unit for the electric field is Newton divided by Coulomb. I'm going to write again. The electric field is equals to force divided by the little q naught. It's force per unit charge. It's the force per unit charge. That is the electric field. Because so it sounds vague, right? What's force per unit charge? What it means is that to Newton's, as the Newton's law say, every time when you have a force, you need to have a two charge object, two charge particles to have a force. Force always come in pair. What electric field is saying is that you just need to have a one charge particle. Whenever you have a charge particle, a solo charge particle, it creates the field around it. It creates the field around it so that when you bring another charge particle in the field, then both of them starting to feel the force. So this little q naught comes by in the field that's created by big Q. Then it feels the force. Imagine something like this. We have a big Q here. And notice that this electric field, sorry about that, electric field I wrote as a vector. It's a vector just like force. It's force per unit charge. So it's a vector because the charge is not a vector. And I'm going to show you the direction. It's interesting how we draw the electric field lines that is maybe a little bit different from how we draw those force vectors. So you got to be careful, but I'm going to show you all those things. Here, so here we have a big charge Q. And then how to find the electric field? What we can measure is electric force. How to measure the electric force? We're going to make this kind of a device made of a stick that has the little spring. All right, the little spring. And this little Q naught is called the test charge. It's typically, you make it to be positively charged and it's a known value. For simplicity, make it into a 1 coulomb, positive 1 coulomb is going to be the easiest to see. So what we're going to do is we bring this little Q naught. Then when you have two charges, big Q and the little Q naught, then they both going to feel the force. So you can measure how much force is applied on this little Q naught, right? If you have a big Q that's also positive, then the force between them, it's going to be, you're going to draw the distance between them, right? This is the R. And the force on the little Q naught goes by the 1 over R squared. And they will be, now we see that this little Q naught is going to be pushed into this direction. That's the force on the Q naught due to the big Q. But you can also see that this force on the little Q naught due to the electric field created by big Q. You see it like here, right? And what happens if you bring it closer? if I bring this test charge now over here, closer with this stick, what do I measure? What is the force now? It's closer, right? So this is going to be the distance. Now it's closer. Does the force on a Q naught increases or decreases? Increases by 1 over d squared, right? So, and then what's going to be the direction? It's still the direction on the Q naught. The force, the direction of the force on the little Q naught is still repulsive. So it's going to be still this direction. But this time it's going to be larger force. So the amount of Q naught hasn't changed. So that means that closer to the big Q, you're going to have a bigger force, which means that you're going to have a bigger electric field. And farther away, you're going to have a less electric field because the force on the Q naught, the charge doesn't change. Your test device don't change, right? Bring it here, here. But then the force changes. That means that electric field around here is weaker and the electric field closer to Q is going to be stronger. So, but even before the test charge, just Q itself, it has the electric field. It has the electric field generated by having a one charge. There's no force until you bring the little q. The little q and the big Q, then you have a two charge object and you're going to feel the force and you can measure the force. And we say the electric field is the force divided by this test charge, the known value. And we say if it's closer, you're going to have a stronger electric field. Farther away, you're going to have less electric field. And then you can put this test charge, this stick with a known charge all around it, right? So this is actually the positive PQ, right? Then what happened? If I put the test charge here, it's going to be pointing in this direction. If I put the test charge here, it's going to be pointing in that direction. It's going to be test charge here, going to be pointing in. All repulsive, right? If I put it, depends on where I put it. Does this make sense? It's repulsive because the test charge is positive. So if you have a big Q, it creates the electric field to have the force on the little test charge always repulsive against it. So it looks like these arms is coming out radially outward. And this line is called electric field lines. You see there's the direction arrows, right? It's outward. So for positive Q, electric field line, so radially, let's say, radially outward. For us, this is a single, right? Single point charge. So if you have a one positive point charge, then that, if I bring the little stick everywhere, you get the force that's coming out always in, you put it here, you put it here, you put it here, you measure the force, and you can see that electric field is going to push this little Q naught in that radially outward direction. So you don't need to have the little charge. Just imagine that there's about having the existence of a point charge. You have a field that's created. You only feel it when you bring the secondary charge. But although we don't feel it, there is a field that's been created by having a point charge. And that's equals to force divided by the test charge. All right? What if this point charge, what if this point charge is negative, minus Q? Okay, then again, I'm going to bring this stick measurement device that has the same little Q naught. This little Q naught is good idea to make it to be positive all the time. It's easier that way. You can use a negative, but it's easier to use just a 1 coulomb and then a positive. Okay, so if it's positive and then big Q is now negative Q, right? It's negative. So which is going to be the direction that's happening on your device, the little device? It's going to be the force between them. It's going to be attractive, right? So the force on the little Q naught now can be drawn into this direction. So let's put all this test charge everywhere. So if I put it here, this is the direction of the force we'll be pointing into. So you see for the negative Q, negative point charge, the electric field, electric field now what do you say? Are radially inward. And I'm drawing in a 2D, but you know that this is happening in all around 3D, right? So if I put the charge here, it's going to be attractive force. So you know that imagine that there's a field line all everywhere that's going in towards the minus Q. If it's a positive Q, you have a field line that's generated everywhere outward. All right. And then to show the electric field line that I just starting to draw, it shows the direction of electric field line. It shows the direction. Direction of electric field, right? If it's inward or outward, that depends on the source, big Q. If big Q is positive, it's radially outward. If big Q is minus Q, it's inward, radially inward. And it shows the electric field line shows the direction. And also, actually, it also shows the magnitude too. It shows the magnitude of electric field. How does it show the magnitude of electric field? Unlike the force vectors, we always draw the longer the arrow, it's stronger, bigger the magnitude. The length represents the magnitude. But for the electric field line, it's not like that, okay? electric field line, the density, denser line region means stronger field. So less dense means weaker. Not by the length of arrows. Okay. So so you can see here, right? If you let's say if I have a sheet, little sheet, unit, one sheet size here, one sheet. How much electric field line passing through per the sheet? So if it's closer together, you're going to have a lot of electric field that's passing through. But then if I put farther away, right? Then you don't have as many electric field line passing through from the source. So you see that either here or the same sheet that's putting maybe like here. Yeah. Same sheet that's putting here. You have it's more dense, closer. Let me see. Sorry, I'm gonna leave the video a little bit. My pen, again, is running out of battery, so I'll be back real quick. Okay, so I'm gonna go back to the screen. Right? And here I mentioned that electric field lines shows the direction of electric field. So the arrowhead is the direction of electric field. If it's a positive point charge, comes out outward. And if it's a negative, comes inward. And magnitude of electric field is by the how much number of field lines passing through per square area, unit area. So if you have a sheet, the piece of paper, let's say like a sheet like this size, then how many numbers are penetrating through, numbers of line penetrating through per area. So if it's a point charge that's closer, you're going to see that a lot of lines are passing through, but if you put it farther away, you know that it's going to be less amount of lines that's going to pass through. So the density of a lines represents the magnitude of the electromagnetic field. It is not that length, okay? So let's see. Let's say we said that if you have just a point Q, right? And then I say, maybe I have for the point Q, maybe I have 1, 2, 3, 4, 5, 6, 7, 8. So maybe 8 lines are coming out. How does the minus 2Q will look like if that's the case? How does that look like? Well, if it's negative, if you put the point charge, positive point charge, it's going to go attracted, right? So it's going to go this direction. But then if you have a negative 2Q compared to Q, you have a twice as much force on a test charge on your little device. So you're going to have twice as much force, field lines too. And I said that for the plus Q, there was 1, 2, 3, 4, 5, 6, 7, 8 lines. So minus 2Q will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I'm having a 16 twice as much field lines going inward. So it goes by the number of lines rather than the length. It's not that minus 2Q doesn't mean longer. That's not it. Okay. It's not by the length, it's by the number of lines. Okay, so that's that. What if you have two charges? What if you have so example or the question? What if you have a plus and minus? What does that electric field look like? So imagine you have a positive test charge here, positive test charge here, positive test charge here. Draw the electric field line. And this plus and minus is called dipole. Okay, so draw the electric field line, E field line of this charge configuration. Which is the dipole configuration. What kind of electric field lines will create if you have a 2 plus 2 charges? That's the same charges but separated by distance. Okay. How about this? Another question, that's question 1. Question 2. What if you have positive, 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 positive? Log 2 parallel plate. That's charged plus Q and a minus Q. How does that electric field line look like for such a configuration? All right, so trying to figure out. So imagine you put the positive Q test charge here. What kind of a force this one would feel? Okay. So I guess that's about it for the electric field. Yeah, I'll see you in a discussion.